All right, so before we left, we were playing around in GDB. We were doing things like using X to examine memory, right? Here we did X/10i in order to look at 10 instructions starting at main. And I'm actually going to go through this little thing. So we know this is example 2 that we're looking at right now. And I want to go through from, to the point where it actually calls stuff. So you'll see that the stack is set up a little differently in GDB. Man, collected everything over here. So, when we look at this assembly code, doing sort of, it starts out looking like it normally does, and then we see that aligning ESP on a 16-byte boundary, like we sort of talked before, or an address that is a multiple of 16. So when we first get into main, we have the address of whoever called main right on top of the stack, right? Got to save DIP. Right. And actually, let me go back to the C source code for just 1 second here. So recall, we're in main right now. And the thing we want to recall about this is that in example 2 in main, we have a single local variable, right? So we have only A, and we're going to pass like argv into A to I, and then we're going to assign the result to A, etc. So going back here, start with our saved DIP on the stack, then push our EDP. All right, and now we get, so at this point we have, EVP and ESP are right here. We also have ESP, but just not for very long. So the next instruction we do is AND ESP with FFFFF0. So right now, inherently, just looking at this assembly code, I don't know if ESP is going to be aligned down or not. I need to know like what the actual address in ESP is in order to know whether it's going to go down, whether it's going to stay the same, is it already aligned, that sort of thing. So what I'm going to do here is I'm going to back up from what I did initially here. First thing I did was break main, right? I'm going to do it a little differently this time. I'm going to copy the address of the first instruction of main. I'm going to quit this out. I'm going to restart it. And then I'm going to do break star and then that instruction of the first actual instruction of main. So this is going to now give me a breakpoint on the push EBP. So I set that. Now I have 2 breakpoints. I have one at 9 bytes in, and then I have one at the very beginning. I can do info breakpoints in order to see where my 2 breakpoints are at the moment. Tell me their 2 addresses again. I can delete the first breakpoint if I want. So delete 1, the number of the breakpoint. Do info breakpoints again. Now I have only the breakpoint at the very first instruction of main. Now I'm going to run this program. It's going to break at the very first instruction of main, and then I'm going to step through 1 instruction at a time in order to see the changes that occur. So I will run. All right, it prints out, some information about what my registers are at the very first instruction. Prints out some stuff about the stack. Right, and then it's going to print 10 instructions. And now I'm going to be stopped sitting here pointing at this one, right? This little arrow sign right here is, well, equals and greater than sign, but it's an arrow. Points at the push EBP saying this is where I'm stopped right now. But we don't know how to step yet. So we need to find out how to step. All right, so that told us about breakpoints. We had break and B, and if you wanted to give an address of something, you would do B star address. Did info breakpoints, and then I didn't put it on there, but delete will delete the breakpoint. I'm just going to go like this. Good enough. All right. So just as some miscellaneous things that Dave Kepler clued me out to, starting in GDB version 7, you actually have the ability to do reverse stepping. So you can be broken at the first instruction of main, and then you can potentially step backwards. I don't know if that actually works if you break somewhere and you can step backwards. I think it's more like if you step forward a couple instructions, you can step back a couple instructions as well. So I actually haven't played with this yet, but just for your own knowledge, GDB does have the ability to start doing backwards type execution. All right, so you can see those two different things. And then, yeah, I guess I want to say, well, I'll come back to disassemblement. All right, so this is sort of that output that we see when we have our stuff, all of our things that, you know, for ESP and all the registers, etc. Just for your own knowledge, when you have the source code available and you compiled it with -ggdb, it will be able to, you know, correspond certain lines of source code like this printf, you know, will correspond to whatever this assembly lines are right now until you get to, so this printf will keep being displayed until you get to the next C line, and then it'll change. So actually, if I go look back in my VM, I should see that up here, this is my source line that I am right now, right? I'm just stepping through this initial prologue code of a main. I haven't gotten to the first line of main yet, where I do A equals A2I of argv of 1. Right? So right now it's saying, well, you're at the source line this because you're still just stepping around. You haven't gotten to anything real. All right, so then we have the step instructions. So back when we were in Visual Studio, we had our little GUI things where we step into, step over, step out of, things like that. Now we have, you know, specific commands to do each of those. So step I is to step one assembly instruction at a time. And so this step I also is always considered like a step into. So if you're on a call instruction and you type step I or SI, it will go to the target of the call, right? So it will step into that call. And then on the other hand, if you're, you know, trying to debug some source code or something like that, and you want to move from one source line to the next, right? Right now we're at a line that says, you know, int main, argc, argv. If I did step, that would bring me to the next source code line. That would be the A equals A2I of argv1. If I did step again, that would bring me to the next source code line. So step is just one source line at a time. But the thing to, you definitely want to think of step I is what you want to use when you want to go instruction at a time. Step is what you want to do when you go a source code line at a time. In reality, if you don't have source code, step will default back to step I, but just use step I basically to separate in your mind. Do or until is basically like a step over at the source code level. So you step over, so it's like go until the next source code line. So it wouldn't go into a call instruction or something like that. Or sorry, it wouldn't go into a subroutine. So if I have, you know, if main's calling subroutine, whatever, if I use until, that will not go into that source for subroutine. So you or until is just sort of a step over. And next I, or NI, is next instruction. So this is the step over instruction. So what we want to, the main things we want to be concerned with, you're probably not going to be doing source code level plugging with GDB that much. So the key ones are step I and next I. That's step into and step over, basically. All right, so now we know step into and step over. We go back to this source code, back to this assembly back here. right? And we want to find out what ESP is at the time when we hit this instruction. So we're at this instruction right now. When I get to that instruction, I'm just going to step over or step into. It doesn't matter for these instructions. It's going to just step 2 instructions. So step I once. Now I'm at this move, right? And I step I again. And now I will be at this ANDing of ESP with FFFF0. So then I kind of scroll up here, and I want to see, what was my ESP. It looks like my ESP at the time when this occurs is BFFF378. So back up on the board, I'm going to use some literal values. Right now, before I execute this AND instruction, ESP right here is, sorry, not 12s now. This again gets into that notion that different operating systems have their own conventions of where the stack is, right? So if you're seeing BFFFF things, right, that's going to be some sort of stack address. And if you're seeing 8 zeros and whatever, then that's going to be some sort of code address, right? So this stuff starting with 80, etc. Find there actually it's 080. It's just dropping the first 0. Things starting with 080, that's roughly speaking where your code stuff is. And things starting with BF, roughly speaking, where your stack is. So this is BF ending in 378. Right? So now I'm going to do this AND instruction. And I said that, anytime you AND something with 0, it's just going to be 0. So we know that we're ANDing this part with 0 and everything else with 1s. So everything that was a 1 will stay a 1. Everything that was a 0 will stay a 0. So this all just, goes back down. So AND that, and all it really does is takes off that last nibble and turns it into a 0 there. So what we see is because of that, ESP functionally had 8 subtracted from it, right? So ESP, after this instruction, is going to be down by 8. So it's down by 8, but it's, not necessarily, like I said, it's not necessarily trying to store any data there. Theoretically, you could use a construct like this to allocate space for data, but in this case, we believe this just to be alignment because the next instruction immediately after that is subtracting hex 20, like our normal way that we allocate space. So anyways, ESP went down to here after we do the AND instruction, right? So it went down by 8, so 4, 8. And then immediately after that, we do subtract hex 20 from ESP. So we allocate space here. Break that up if I want, but ESP is now here. If we wanted, we could think about this. This is EBP minus hex 28 or something like that. But I don't know if this has any bearing, but put it there in case it matters. ESP is not there anymore. This we're going to call padding right here, or we'll call this like aligned space. I don't know how to spell aligned. How do you spell aligned? A-L, is there 2 L's or 1 L? 1 L? All right. A-L. N, there's no H's. Aligned space. All right, so this right here is kind of, whatever it is. We don't care about this aligned space. It's just something that happened because of that alignment AND. All right, and then this is going to be our local variable space, potentially. Well, okay, so I won't even say it that way. This is going to be more than our local variable space, right, obviously, because we only have a single int a. Right, so somewhere in here there's an a, and then we don't know what the rest of it is yet. So now we're going to walk through the rest of the instructions, see what's going on and why there's this extra space here. All right. So I'm going to step Over that, that aligns it down. So now we see ESP is 370, right, ending in 370. Going to step over the next instruction, which subtracts hex 20 from ESP. Right, now it's down even farther. Now it's 3F350. All right, and so now what do we see next? All right, let's just kind of eyeball this next sequence of instructions. We see something leading up to the call. So we probably have an idea that something is going to be pushing stuff onto the stack for that A2I. Last time we saw this, we were all big into that picture of how do you actually find the argv of 1 and things like that. So we're probably, again, going to go out and find our argv of 1, that address of the string kind of thing. And so if we look at this, what we see is EBP plus C. Okay, what do we know about EBP plus things? What kind of variable is that? Yep, parameter passed into the stack. So here's some sort of thing which parameter passed to the stack of main. Well, we didn't draw it up here yet, but what parameters were passed to the stack on main? So what's immediately above the saved EIP? Eric? Yep. argc. argc, which we're just going to assume is 2 here, even though I forgot to give a parameter to this, and so it's going to crash. Well, I'm going to restart it just so that we can actually see the 2 in a register. All right. 1, 2, 6. Go. Now I'm going to do step I. 1, 2, 3, 4. Step 5 and 4 instructions. Success. So you can actually say, I want to do multiple steps. So I did step I4, and now I'm back here at that. So EBP plus C, right? So, well, first I just asked, what's that, what's the thing immediately above the saved EIP? And Eric said that's argc, that's correct. And what's immediately above that? Katie? What's above argc that's passed into main? Next up is that argv, right? And that argv was like a char star star kind of thing, right? We passed the arguments into main, right to left. It was main of argc space argv, and the argv was like whatever it was. Character, pointer. That should be on the other side. Who cares? All right, so this instruction right here, we're going to do EBP plus C. EBP is right here. Plus 4, plus 8, right? We said plus 8 is always the first parameter. Plus C, that's the second parameter. So we're going to get the pointer out of here, and we're going to store it into the EAX register, right? So we said before when I had this picture down lower, argv points up to an array of pointers, right? And so we knew that like the first element of that array is not what we want. We don't want argv of 0. We want argv of 1. So we have to step 1 into that array. That's kind of that plus 4 coming up next. But let's just do this. Step I over that, and we'll see what's in EAX. All right, so EAX has what looks like a, so this is where I said before I'd never done this sort of thing, digging into the argv and things like that on Windows, so I didn't know whether, that C, whatever it was, address was anything particularly indicative, but I do know that on Linux, your argv, your argc, and your environment variables and all sorts of other stuff is up just further on the stack. So the kernel puts that stuff like the environment variables on the stack. Then the kernel puts like the argument vector, and then it puts, things like that. So anyways, we can see that this pointer, which was in, this thing which was the third thing in here, this pointer to an array of pointers, what was actually inside that memory range was BFF ending in 14. Right, that was what was actually in memory. So that previous instruction was an RM32 form because it had the little parentheses on it, right? Parentheses around EBP. We do EBP plus C because we got our nice displacement off to the external to the parentheses, but So you take EBP plus C, calculate that as an address. That was the address in there on the stack. And then we go dereference that and grab the memory out of that address, stick it in EAX. That's why EAX is now FFND. Right? Because somewhere up here on the stack, well, there it is. Right? Right there, that's argc on my stack. That's argv. That's a, what is that? Saved EIP. That's a saved, and note this saved EIP, it doesn't look like our EIPs, right? Like, that doesn't look like an 80 whatever. This is the saved EIP of the guy who called main, right? So it's somewhere else in memory. Pretty sure that's the dynamic linker. And then this is like a saved EIP, or saved EBP, and then this was like alignment junk, and then there's X20. Right, so 4 times 4 hex 20 is 32. Well, is that right? 4 times. Whatever. All right, anyways. So the next thing we're going to do, we have the address that was stored in that argv pointer, right? So we have the pointer to that array of pointers. But we don't want to pass argv of 0 into A2I. We're passing argv of 1. So, you know, we're going to step one element into that argv array, right? And so we're just taking EAX, which is this 424, and we're adding 4 to it, then we're storing it back into EAX. So it'll turn into, EAX will turn into 428. Step 5. EAX is now ending in 428. And this is what we're saying is argv of 1, which should be a pointer. It's a character pointer which points at some string, right? It's the parameter we passed in. Now, if we want to examine that memory with GDB in order to like see, is this actually the string for that parameter that we thought it was? We can use that examine memory with the format string, like with the format specifier of S, right? So x/s tells us to go to memory there and look at it as if it were a string. So I'm going to copy that, x/s it, paste the address, and that's a failed log array. There we go. So I guess I needed to add the little star on there again. So yeah, that's actually, because this is actually pointing at some other location memory, right? So again, just to make this quick, we have argv is a pointer to a pointer, right? This points up somewhere to this array. This array, each of these things is a pointer, right? So this is a pointer, that's a pointer, and, you know, this is argv of 0. This is argv of 1. Right? And each of these, though, points to some string, right? Somewhere else. And this could be, you know, the string, you know, ASCII, whatever an ASCII byte is for 2, right? So I can't think of it off the top of my head, but I can totally find it out. What it was telling me when I didn't put the star in front of the address is it was just literally going to, so if we said that this right here, so if this was BF ... 424, and this was BF ... 428, all right, so the question was, you know, what was it actually displaying when I didn't put that star on there, right? It was basically just going to memory at the address that I gave it, treating that so as a sequence of ASCII characters, but it wasn't actually doing it like it was probably putting it in octal, because that sequence is D5. Let's see if I can do octal. There we go. Oh, he knows octal. Yeah, so for whatever reason, it was defaulting to octal at that moment, and therefore, It was just saying, like, this is an octal 325, aka a hex D5. And as a character, XD5 is like, I don't think it's anything because ASCII characters are all less than 7F. So it's a non-printable character. But I can try like this C. I guess I didn't show you C and I didn't show you octal. That's what the man page is for, right? So I mean, you can't print this out as a character, for instance, which would have normally done it as like an ASCII character because it's not in the printable ASCII range. I don't know why it loves octal right here, but pretty sure it probably has to do with the defaults, which are stupid. Anyway, so when I put the star on there, right, then it's saying like actually dereference this. So realistically, what I should have done was, you know, recognize that the next instruction was dereference EAX and put that in. That's the address of the actual string, right? So all I had done thus far is I had gotten a pointer. Let's see, right? So this gave me a pointer to this memory, right? So ending in 428, that's not my string. That's where I have the address of the pointer to the string, right? That's why the next thing is saying, take out whatever's in here and put that into EAX because that's the pointer to the string. That's the thing which points up there. So the next instruction, if I would do that without the star, it would work. By putting the star in, I like forced it to dereference it once myself. So let's execute this move from memory pointed to by EAX. Dereference this. This is an RM32 form. Dereference it, stick it into EAX. So whereas EAX right now is pointing at this 428, we want to get the thing out of that memory and then put that in EAX. All right. So did that, got ending in 5D5. So up here somewhere is 5D5. Got 5D5. That's where there's actually a sequence of characters, one at a time, ending in a null character. Right? And so if I did this now as a string, if I did x/s and then that, right, then that's going to say if I go to the address ending in 5DF or 5D5 and I print one character as an ASCII string, 1 byte as an ASCII string, 1 byte as an ASCII string, and finally I hit a null terminating character, then this is a string. So again, I could look at that like, you know, one character at a time if I wanted. I could say the character literally at 5D5 is 2. One at 5D6 is 5, 7, finally 8, right? Ending in a null character. Okay, so that's my string. Anyways, so what I have in EAX right now is the value that came out of here. And that's the pointer, 5D5. Right, so this was 5D5. I took that, I put that into EAX. And what am I probably going to do with that if I want to like call A to I and I want to pass it argv of 1? That. What do we think is coming up? What would you expect is coming up next if I'm pushing, if I'm going to call the thing, right?
Sorry, this is a glitch. I was scrolling through some of yours.
Okay. So I've got this value that's stored in argv of 1 in EAX, right? And I'm building up to a call to A to I. So what do I expect is going to happen next? Right. So you'd expect that I would do a push EAX or something to that effect, right? Not so. No. It's, yes, it is, but it's not. So this is where the weirdness of GCC's allocation of memory comes in. So we saw before that it allocated a bunch of space that seemed like too much space, more than we needed. If we look at the next instruction, we see not a push EAX. We see a move EAX to memory pointed to by ESP. ESP is down here at the bottom of that big blob of memory that I allocated. Some big blob. We did ESP minus hex 20. All we know is there's some hex 20 space here, right? And now what this is telling me is take that EAX that I have, my BFF ending in 5D5, and stick that into memory wherever ESP is currently pointing. ESP is pointing right there, so I'm going to do BFF ending in 5T5, put it right there, 4 bytes, BFF 5D5. Right? So I didn't move the stack. I didn't push anything on, right? I didn't push to make the stack pointer go down or anything like that. It's like it creates all the space it'll ever need for locals and maybe parameters that it's going to pass to functions. Creates it all in one fell swoop. And then it goes ahead and anything it needs to pass to functions, it puts it onto the stack here or there, right? And that's functionally the equivalent because once you go ahead and do that call, you know, the top of your stack is right here. And so what's going to be here next? You know, saved EIP. Right? So I call A2I, and I have saved EIP, which is going to be, what's it going to be here? Anyone? What's going on the stack? Say it louder. Yep. 80483DA, right? The instruction after the call instruction. So that's 483DA. Dot, dot, dot. 483DA. For people on the video. Wait. All right. So when I do the call, right, that's going to push the save thing. We're going to treat, just like we did last time, we're going to treat A2I as some black box. I put things onto the top of the stack. I need to make sure that the top of the stack has my parameter I'm passing to it. And then I call it. And then I get back some number in EAX, right? So I'm going to treat this, you know, we'll say we called it. It did its thing with its stack frame. And finally, A2I returned. There's no more saved thing. We're back to the top of the stack, being right there. And so in order to do this, I'm going to use the next instruction, the next instruction. So right now I haven't pushed the thing on this stack yet, so I'm going to do that first. The step I. All right, that pushes my 5D5 onto the stack, just like we showed on the picture. All right. Then I'm going to next I over this call instruction. All right? And then that's going to get me to the instruction immediately after the call instruction, right? And what do I see in EAX, right? What's my output from the A2I? It's hex 100, aka that 256 decimal. All right. And then now it turns out, let's see. So now what are we going to do? Well, what did we do with our return value from the A2I? We assigned it to A, right? A equals A2I of argv of 1. So now we see something interesting. EAX, which is our return value, is being put into ESP plus hex 1C. Well, this entire big blob was hex 20, right? So hex 20, little math here. What's hex 20 minus 4? Right, for instance, what's hex 20 minus 4? 1C, 12 plus 4, carry the 1. Right? So ESP still points right here. This is still on the stack. And we know this went down 20, and we know we want to now go up 1C, right? And then that leaves us pointing at this right here. So it's like EBP minus 4. Well, it would have been EBP minus 4 if we hadn't had this alignment, right? So rather than doing an EBP minus something, because they don't know how much it would be EBP minus, right? I said before, until we actually saw what these literal stack values were at the time of this, we didn't know whether it was going down, whether it was staying the same. All of a sudden, now this is using ESP relative addressing rather than EBP minus, EBP plus. Okay, so ESP relative now, this is ESP plus 1C. This is our, int a equals x100, right? So int a is stored in memory here, sort of at the top of the local variables as we would expect. But it's not using EBP relative things, presumably because of this alignment thing that occurred. And they don't know how much it's going to be aligned because they don't know, for instance, how much stack space the previous function used, right? The previous function could have been aligned and then pushed one thing onto the stack, and then it's no longer aligned. So this alignment thing would subtract a certain amount. So when they're using that alignment sort of thing, they start using this ESP.
So if alignment matters, why isn't Windows alignment doesn't matter?
Well,
why is Linux kept?
I can't speculate as to that. As I believe I said yesterday, the whys and the wherefores of compiler operators, compiler programmers are unknown to me. Sometimes they'll choose to go with some guidance. Sometimes they won't. Maybe they'll have done their own performance benchmarking where they said this doesn't care. Whereas these people didn't do performance benchmarking and they just said, well, the spec says align it, so we'll do it. Right? I would guess if Windows isn't doing it, it probably doesn't actually matter to any significant degree because they do care about performance a lot. So. Okay, so what do we see? Take an EAX, sticking it into ESP plus 1C. That's what we're going to call A, right? That's our variable A. And then immediately after that, we see another one of those silly little things where we move from ESP plus 1C immediately into EAX, right? So, but we already have that in EAX. That's what, I don't care what's in ESP plus 1C. We know that's already what was in EAX, right? So, point is, it's being very, just very simplistic about it. What are we doing after the, assignment, right? A2I return address goes into A. Now we're going to read whatever's in A, push it onto the stack in order to call subroutine, right? Then we're going to go find argc, push that onto the stack, call subroutine, right? So it's just going to go in, say, hey, I got to get A, going to go get it out of memory. Not keeping track of the fact right now that it has it in memory already, register. So it gets it into the register, and then it's going to put that to ESP plus 4 now. All right, so let me step through this here quick. All right, so put it into memory, get it back out into EAX. Oops. All right, so EAX X100. Wait, did I go far enough? Yes, I did. Okay. EAX is hex 100. And now the thing it's going to do with it is it's going to, there's an RM32 destination here. EAX goes into ESP plus 4. Calculate the address ESP plus 4. ESP still points here at the bottom. Calculate that plus 4. Stick this into memory at that location. We have a destination which is memory, right? So this is ESP plus 4 right there. Take our hex 100 and put that there, right? And so we can see, right, we're not pushing stuff onto the stack, but we are kind of probably putting it in the right place, right? The second parameter goes at ESP plus 4. First parameter is probably going to go ahead and overwrite whatever's at ESP. So, do that. Here's our stack right now. It's still down here at 350. Still got that on the stack. I'm going to execute this next instruction. Take EAX, which is hex 100. Put it into ESP plus 4. That's right there. And that should be hex 100 after I step over this. Bam. Hex 100, right? ESP plus 4. All right. Now, what's the next thing doing? Well, we've got EBP plus 8. EBP plus something are the function parameters passed in. EBP still points up here. Plus 8. That's argc. That's the second thing we're passing in. All right. So you can see we're going to get that into the register EAX. And then we're going to push that. We're going to take that register and write it to wherever ESP is currently pointing. That's right there. Go ahead and write argc, which is 2, onto ESP, right? So that's the second instruction up there. So first instruction, get 2 into EAX. Step I. All right, EAX is 2. Next instruction, move EAX to ESP. Step I. Okay? The top of our stack is now 2. So we've got our parameters pushed, quote, pushed onto the stack because the top of the stack has our first parameter, next to top of the stack has the second parameter. And now we can call subroutine. I'm not going to go into it, right? We know it goes in there, it multiplies 2 times. Well, okay, I will go into it because we saw that it generated different code than we saw in. All right, I'm going to step into this call instruction. That's going to put me at, the start of subroutine. You can see up in the source code view right there, it says int sub x and y. Got a standard function prologue. I'm going to just step over those 2 quick. Step I2, all right, to get past those. All right, now what do we see? We see EBP. So, just to do it quickly, we're down here. We've got a saved EIP. Right? We called sub, got the saved EIP. First thing it does, pushes the saved EBP. I hope this repetition is helping make it so that if called upon to make your own stack pictures, you could recognize that at least there's going to be some sort of saved EIP, saved EBP kind of thing going on, potentially. All right, so anyways, EBP points here now. We're past variable. All right, so we're now in subroutine. We're accessing EBP plus 8, right? Well, EBP plus 8 is always the first parameter to our function. That's 2. Put 2 into EAX. All right, and now here's the interesting thing where they're doing things differently, right? So when we get into subroutine, in that source code view, right, this was X, this was Y, right? In subroutine, it considers its parameters passed in. First one is X, the second one is Y. And what are we trying to calculate? 2 times X plus Y, right? So whereas previously they did a single LEA instruction, which, right, was the LEA functionally did LEA of whatever it was, Y plus X times 2, right? That's kind of what we saw before. Right, this time, no. We get to this EBP plus 8 into EAX, and then we just add EAX to itself, functionally becoming 2X, right? 2X, we got 4 there now, and then you can see EBP plus C, which is the Y. Go ahead and add directly from memory. So this is an add where we're using the RM32 form. We already have 2X in EAX, and now we're saying our Y is in memory at EBP plus C. Just take it directly from memory, add it into EAX, store the result in EAX. Now EAX holds 2X plus Y. And then tear down. Pop EBP, etc. So now I'm going to try turn from this function. We'll see if this works. All right. So there's this finish command that not in your slides, but if I do the finish, this is the step out of, basically. So I'm in subroutine somewhere right now, and I want to step out, so I'm going to try finish, except a little weird sometimes. Okay, well that did step me out of subroutine, right? And it stepped me into main. Let's see if it put me to the right instruction. There's sub. Oh, okay, here's what I know right now. It brought me back to a leave and a return in main. I'm going to do a quick x/10i of main. Yeah, so not quite. Let's skip the, no, yeah, that's right. Okay, so if I return from that call to subroutine, right, the next instruction would be a leave, and then the next instruction would be a return. So I just stepped out of sub, and now I can go ahead, do my leave, which is, right, so what is leave? Move ESP, which is down here somewhere. Right, so when I got out of the subroutine, ESP is down here again. Move ESP to EBP. ESP, right? That like wipes out everything up to there. leave destroys all that, and then it does pop EBP, destroys that. Then we're just back to this, return, destroys that, and we are out of main. And it is the caller's job to clean up those parameters that he passed, right? We're not a standard call function. All right, so that's going through an example 2 in GDB, right? So the key commands are, setting our breakpoints, setting our displays, things like that, right? So display, we just set all those up. You just do it once in a command file, you're done. And then just step into or step over, right? So step into is just step I, and step over is next I. So those are the main things. And the examine memory, right? So X means go to memory at that location and treat it like a string or a character or a D word or something like that. All right. So that was going through a simple example in GDB. Any questions about executing stuff in GDB? I'm sure I have more commands that I probably forgot to tell you. Now we're going to go back and learn about. But any questions thus far?